Chapter 1. The Beginning. Teaching Computers to Think. Imagine you're a teacher in the 1950s and you have a very special student, a computer. This student is incredibly fast at calculations but has zero common sense. Your job? Teach it to make smart decisions. This is the story of machine learning, humanity's quest to teach computers to learn and think. Today, that same idea powers ChatGPT, recognizes your face on your phone, and even drives cars. But it all started with one simple question. Can we teach a computer to find patterns? Our journey begins with the most basic pattern of all, a straight line. And by the end of our story, you'll understand how we got from drawing lines to creating artificial minds that can write poetry and solve complex problems. But real quick, if you want more tech stuff explained without the BS and boring parts, hit that subscribe button and ring the bell. I drop videos every week breaking down complex tech into stuff you can actually understand. Like seriously, my mom watches these and she gets it. All right, let's jump in. Let's start our adventure. Chapter 2. The Foundation. Linear Regression. Our story begins in the early days when statisticians discovered something magical. Imagine you're running a lemonade stand, and you notice that on hotter days, you sell more lemonade. Linear regression was humanity's first attempt to teach computers this simple wisdom. Find the line that best explains the relationship. Picture plotting dots on a graph, temperature on one side, lemonade sales on the other. Linear regression draws the best possible line through these dots, essentially teaching the computer to say, for every degree warmer, expect to sell 3 more cups. This was revolutionary. For the first time, computers could predict the future based on the past. This simple idea became the DNA of all machine learning. Even today's most advanced AI systems use this basic concept deep in their cores. But soon, we faced a problem. What if life isn't just straight lines? Chapter 3. Beyond straight lines, logistic regression comes to help. Real life isn't always about predicting numbers. Sometimes we need yes/no answers. Will it rain? Is this email spam? Will this patient get better? Enter logistic regression, the hero that taught computers to make decisions, not just predictions. Instead of drawing straight lines, it draws S-shaped curves that give us probabilities. Think of it as upgrading from, I'll sell exactly 47 lemonades, to there's an 80% chance I'll have a busy day. This was huge. Now computers could help doctors assess risk, help email systems filter spam, and help businesses make decisions under uncertainty. But we quickly realized another limitation. What if the patterns are more complex than any single curve can capture? Chapter 4. Here comes the wisdom of crowds, decision trees and random forest. Sometimes the smartest approach is the simplest. Decision trees work exactly like how you make decisions every morning. Is it raining? No. Is it cold? Yes. Then wear a jacket. This chain of simple yes or no questions became incredibly popular because anyone could follow along, like playing 20 questions with a computer. But imagine if you made all your life decisions based on just one friend's advice. Sometimes that friend might give you terrible advice, right? A single decision maker had the same problem. Picture this. Your computer learned the rule, people who buy lots of ice cream are happy customers. But then it meets someone buying ice cream for a big party who's actually about to cancel their account. The computer gets fooled by this weird situation and starts making wrong guesses about future customers. So scientists had a brilliant idea. What if instead of asking just one advisor, we ask 500 different advisors and let them all vote on the answer? Imagine having 500 different advisors, each looking at the problem slightly differently, all voting on the best answer. That's how random forest was born. This ensemble approach became one of the most reliable methods in machine learning and remains popular in 2025 because it rarely makes catastrophic mistakes. But as our problems became more complex, like recognizing handwritten numbers or understanding human speech, we needed something more powerful. Chapter 5. Learning from Neighbors. K-nearest neighbors. Sometimes the best way to understand something new is to compare it to things you already know. K-nearest neighbors, KNN, embodies the wisdom, tell me who your friends are and I'll tell you who you are. When facing a new email, KNN looks at the 5 most similar emails it has seen before. If 4 out of 5 were spam, it says this is probably spam too. It's beautifully simple and surprisingly powerful. The algorithm literally remembers every example it has ever seen and makes decisions by finding the most similar past experiences. But this simplicity came with a cost. It could be slow and sometimes fooled by irrelevant similarities. We needed algorithms that could find more sophisticated patterns. Chapter 6. Finding the Perfect Boundary. Support Vector Machines. Imagine you're a referee in a soccer game and you need to draw the perfect line to separate two teams' territories. You want the line that gives both teams the maximum fair space. Support vector machines, SVM, do exactly this with data. They find the perfect boundary that separates different groups with the largest possible safety margin. What made SVMs truly special was their use of kernel tricks, mathematical ways to handle complex curved boundaries. It was like giving the referee the ability to draw not just straight lines, but curves, loops, and complex shapes to perfectly separate the teams. SVMs became the gold standard for many years, especially when working with complex data. But as our ambitions grew, like wanting to recognize faces or understand speech, we needed something that could learn even more complex patterns. Chapter 7. The Brain-Inspired Revolution, Neural Networks. This is where our story takes a dramatic turn. Scientists looked at the human brain and asked, what if we could copy how neurons work? The first neural networks. Early neural networks were simple. Imagine a basic calculator that could combine information from multiple sources. If you wanted to recognize handwritten numbers instead of looking at just individual pixels, the network could learn to combine pixels into meaningful patterns. But here's the problem we faced. Simple neural networks could only learn basic patterns. Imagine trying to recognize your friend's face by only looking at individual pixels. Impossible, right? You need to understand that pixels form lines, lines form shapes, shapes form facial features, and facial features form a recognizable face. Single-layer networks couldn't handle this step-by-step learning. They were like trying to jump from "I see dots of light" straight to "that's Sarah," without understanding anything in between. But the real magic happened when we started stacking these layers. The deep learning revolution, learning step by step. Deep learning was like discovering that you could stack many floors in a building. Each floor learned different levels of patterns. First floor recognizes lines and edges. Second floor combines lines into shapes. Third floor combines shapes into objects. Top floor recognizes this is a cat. This hierarchical learning mimicked how human vision works, and the results were stunning. Suddenly, computers could recognize faces better than humans, understand speech, and even drive cars. The Transformer Revolution. Then in 2017, everything changed again with transformers. These networks learned something called attention, the ability to focus on the most important parts of information while understanding how everything connects to everything else. Imagine reading a book where you could simultaneously understand how every word relates to every other word in the entire story. That's what transformers do with text, and it's why ChatGPT and Claude can understand context so well. Chapter 8. The Probabilistic Approach, Naive Bayes. Not every solution needed to be complex. But while everyone was getting excited about complex neural networks, some smart scientists said, wait, do we always need rocket science to solve simple problems? Naive Bayes brought us back to basics with a simple question. Based on what I've seen before, what's the probability this is spam? It works like a detective collecting evidence. Each word in an email is a clue. Free appears in 80% of spam emails. Money appears in 60% of spam emails. Urgent appears in 90% of spam emails. Combine all the clues and you get a final probability. It's called naive because it assumes all clues are independent, which isn't true. But it's so fast and effective that it's still used everywhere in 2025. Chapter 9. Discovering Hidden Patterns, Unsupervised Learning. So far, our story focused on learning with a teacher. We always knew the right answers. But what about discovering patterns no one has seen before? Clustering, finding hidden groups. K-means. Clustering is like being a detective who walks into a room full of people and says, I bet these people naturally form 3 groups based on their similarities, without knowing anything about them beforehand. This is how Netflix discovers new types of viewers, how scientists find new species of stars, and how marketers discover customer segments no one knew existed. Dimensionality reduction. Seeing the big picture principal component analysis, PCA, solves a different problem. I have too much information. What really matters? Imagine you're describing people using 100 different measurements, but you discover that just 3 combined measurements, like size, age-related features, and lifestyle, capture 95% of the important differences between people. PCA finds these magical combinations automatically. This became crucial as we started dealing with massive amounts of data. Sometimes you need to step back to see the forest, not just the trees. Learning through trial and error. Chapter 10. Learning through trial and error, reinforcement learning. Our story takes another exciting turn with reinforcement learning, teaching AI like you'd train a pet through rewards and consequences. Imagine teaching a dog to fetch. Good behavior gets treats, bad behavior gets nothing. AI agents learn the same way, trying different actions and getting feedback on their results. This is how AlphaGo learned to beat world champions at Go, how AI learned to play video games better than humans, and how ChatGPT learned to give helpful responses through human feedback. In 2025, reinforcement learning powers AI agents that can use tools, make decisions over time, and even learn to control robots in the real world. Chapter 11. The Modern Era, Foundation Models and Generative AI. We've reached the climax of our story, the age of foundation models. The everything models. Instead of training separate AIs for each task, we discovered we could create massive models trained on nearly everything: text, images, code, and more. These large language models like GPT-4, Claude, and Gemini became like super-educated humans who could quickly learn any new skill. The creative revolution. Generative AI models, diffusion models, and multimodal AI. Diffusion models learn to create images by starting with noise and gradually removing it until a perfect picture emerges, like a sculptor removing marble to reveal a statue. Multimodal AI can now see, read, listen, and speak all at once. We've created AI that doesn't just process information, it creates, imagines, and helps us think. Chapter 12. The Present and Future, 2025 and Beyond, Edge AI, Quantization and Distillation, RAG. Edge AI means these powerful algorithms now run on your phone, your car, and even tiny sensors. Quantization and distillation make giant AI models small enough to work anywhere while staying intelligent. Retrieval Augmented Generation, RAG, combines the creativity of large language models with real-time information, like giving a genius the ability to instantly look up any fact. Choosing your algorithm. Understand the complete toolkit. Start simple. Linear logistic regression for basic patterns. Need reliability. Random forest for most structured data problems. Complex patterns, neural networks, and deep learning. Understanding text creating content. Large language models. Finding hidden groups. Clustering algorithms. Making decisions over time. Reinforcement learning. Working with limited resources. Traditional algorithms like SVM or naive Bayes. The complete journey, what we covered till now. Journey. Till now, we started with teaching a computer to draw a line through dots. We end with AI systems that can write poetry, create art, solve complex problems, and even help us understand the universe. But here's the beautiful truth. Every breakthrough you hear about, from ChatGPT to self-driving cars, is built on the same fundamental ideas we've explored together. Linear regression still lives inside neural networks. Decision trees still power recommendation systems. The wisdom of crowds still makes random forest one of the most trusted algorithms. You now understand the complete story of machine learning, from the first simple patterns to artificial minds that can think, create, and dream. And this story is still being written, with each new breakthrough building on the foundation we've explored together. The future of AI will bring even more amazing developments, but now you have the knowledge to understand and be part of that journey. Like and subscribe.